Welcome coders, hang around if you want to know how this effect is done. Hi everyone, this is actually a port of a very old example I wrote in PlayBASIC, and the example was written, I think it was tagged as being 2001. Yeah, 14th of May 2001, so almost 21 years ago. Let's take a look at the original. Here's the original code as I ported it from the PlayBASIC code. Now PlayBASIC has very rudimentary two-dimensional support, and I could port this example because PB and PlayBASIC pretty much overlap in this area, so we're not using any features that PB doesn't have. The downside of that is that PlayBASIC doesn't have things like types, so we have to emulate types using two-dimensional structures. If we page down the bottom here, we can find this out. So what I'm doing here is I'm defining a bunch of variables that are offsets into a second dimension, and it's kind of like having, these are like fields in types pretty much. So then later on I dimension an array. I use on the left hand here is the object I'm interested in. On the right hand is the data that I'm interested in. So here I'm setting the reset timer field, then the update timer, then the change over time. Anyway, let's run this example and check it out. Bit slower to start up, and we have less stuff on screen, so it's less crazy. And we have no effects, pretty much. But in principle, the routine's the same. The lines are really a series of points. All we're really doing is we're moving the first point in that line, and then all the old positions get passed down to the previous location for as many points as we want to store. So each line has a list of these points that, where we are this frame, where we are last frame, the frame before that, the frame before that. I think it's up to about, we'll have a look. We'll just check. All right, so each line's allowed to have 100 points in it. So there are 100 line fragments for each one of these lines. We have 50 lines in the scene. So if we bump this up a bit, we'll get something more like what we have in the last version. We'll have 200 lines and 100 fragments each. The pause at the start's actually building the palette, because we're replicating how it was done in PlayBASIC, which I've optimized out of the other examples. I still quite like the effect. Now, because the points are roaming around in effectively, I think it's a cube or a rectangle of 3D space, this volume of 3D space, they're allowed to move in any direction until they reach the borders of this space. Then they're reflected back in, the same as what you would do if you were bouncing within two-dimensional space. So if you've got a character moving around the screen, you want it to bounce off the walls when it hits the one of these edges, let's say the top or the bottom or the sides or whatever it's going to be. We take its current speed and reflect it in that direction. What we're missing out in this version here is you'll notice that the lines are kind of erratic, and that occurs because every couple of frames we are randomly changing the direction that it's moving in. So we don't get these kind of nice sweeping patterns. Generally, we get kind of harsh looking. Some of them look okay, but other ones don't. Now, when I've updated the code, actually, we'll just quickly address that startup. So we're building a palette. I think if we just put a lock buffer at the start of that, it's drawing a bunch of color, just dot plots pretty much. I think that's how it's working. Yeah, dot plots for each row. So the lines are made up of these color fades over time. So the first point is the brightest color, and then it's slightly dimmed for the next point, slightly dim for the point after that. So we get this kind of trailing effect, or like a streamer effect, really. Let's run it again and see if that's, yeah. Alright, that's the original version of it. The version 2, I'll just load that for us. Load version 2. I made a note here, there's a strange bug I posted a video about as well. It gives a weird effect. Let's check out the basics of this demo. We've got 200 lines and they're 200 segments in length. And if we run it, we've got these kind of glow balls that appear to be on the heads of each file line, and we've got some blending occurring, of course. But the weird thing about this demo here is you see this, how the lines align themselves along these cube edges. And this occurs because the clipping is actually, the speed is being randomized and calculated, and eventually the characters are leaving the constraints of the region, but they're being clipped back into it, but never actually coming back into the interior. I'll just show you. So we set up a bunch of limits for 3D space. It's this cubic volume. Now, they've got the same structure here. We've got these, we do have one new thing here, that's right. Speed now is represented as two different values. We have the old speed and the new speed. So this update timer counts up from 0 to the next change of direction. And this reset timer here I think it's randomized. Every time it counts down, it resets itself to a different length. So it might be quick to go from one direction to another, or it might be slow. So the actual rendering process itself is drawing the stuff to screen, but we have the initial setup code here, which generates the each one of the 200 objects that we established that are in the scene. They're given a time until the next reset when they change direction. They're given a standard direction, so they're all kind of moving in a positive direction up front. We're giving it a position within the constraints of the world. We're setting all of the positions in its tail. So, because initially when it starts, its initial position and its old positions they won't have been set yet, so they'll all have been 0. So otherwise we would have all those points connected back to 0. If we leave this out, for example, we'll get a whole bunch of points connected back to this origin point for that first probably handful of frames. Let's have a look. So actually it made quite a nice effect, actually. I wasn't expecting that to work. But we still get the same sort of buggy approach where they get stuck on the boundaries. Let's go back through the routine. We'll reinsert that there. Might try that with the other version. That's our setup code for each line fragment, and then what we're doing is we're rotating them in 3D space. But it's a very preliminary sort of thing. We're just doing a rotation of all the vertices in the scene at whatever our orientation is, and we're just pushing the scene at 200 units away from the camera using a projection value of 400. So here we're doing the rotation, taking because originally the points in space, it's very static. So if you got the characters moving in space and the whole volume rotating as well, it's much more appealing on the eyes. So we're doing a rotation of the point here, calculating the depth, which I don't think we really need. Projecting it, sorry. Oh, yes we do actually. Projecting it, storing it in here. So we actually have two buffers by the looks of things. We've got, for each line, we have a series of line segments, and we're rotating all the points in that segment as well. So we have its position in 3D space, which is non-rotated, and a rotated version of that ready for rendering later on, which is what the pass down here does. So we rotate all the points, and we go, okay, let's draw the thing to the screen, and we can draw them in any order we like because we're doing an alpha addition of these characters, of these line fragments. What that means is that if you think about the just addition in general, it doesn't matter what order you do those things. If you have a color that's set to RGB 100, 100, 100, and you add another color that's RGB 10, 10, 10, the resulting color is 110, 110, 110. Now if I swap the terms around, if I have RGB 10, 10, 10, and add RGB 100, 100, 100, you would get RGB 110, 110. That's the beauty about doing alpha addition. We're just adding this new pixel over the background, the backdrop buffer. Now to do that in PB, we're using we're rendering to an FX image. Hopefully you're aware of that stuff. This mimics the screen size. So we're drawing off to this off-screen buffer. As you can see here, we're setting up rendering to this thing here. We're processing our lines, and we're rendering the lines here in 3D space. Before this, we've set the rendering, the ink mode, to alpha addition. So if you go to ink mode here, hit F1, takes you to the help file. There's a bunch of weird gobbledygook down here, but this is about the kind of blending modes or blending methods that are available. So the defaults are just a normal render, and you've got these effects ones at the bottom. So 64 is alpha addition. So we're whatever color, if we're drawing a line to the screen, we're drawing that line in RGB 10, 10, 10. Then for every dot on the screen that's being drawn by this line, that dot's being added to the background, to the RGBs of the background color, and it's increasing them all by 10, 10, 10. Now, if we kept doing that every frame, it wouldn't take long before the frame is just all white. Every pixel is completely saturated to its highest possible value of 255. To counter that, what we do is rather than clearing the screen, we do a multiplication of the screen. I'm doing a slightly biased one here. So when I take the pretend screen image, I draw that to the actual screen, but I do it with a multiplication. So I'm multiplying every pixel in the image by this RGB, these components here. And if I do the multiplication and each one, if we have 255, we multiply it by 255, we'll get pretty much the entire pixel retained. But here, you can think of these as like percentages. So if we have an R value of 200 and we multiply that by our, on the output buffer, it's going to give us about 75, probably not 75%, yeah, probably, let's say about 70% of that original red color will still be there on the output. So we can scale down the old pixels over time. And to sort of show you that, we can do that here actually. We just draw the image, image screen, just draw it false, get rid of that completely, and it won't take long before the screen will just be white. So without the combination of the alpha addition effect and depreciating those pixels or scaling the pixels down, we don't really have much of an effect at all. I mean, you could just do, you know, go up to here for a second. We put a CLS in here. Draw the image. So each frame, we're starting from a black image all the time and adding our lines and our circles to it. Now that works pretty well. It's still an interesting looking effect, but we don't have any of the retention of data over time, making the effect look more appealing. Restore it back to how it was. This is not the final version, of course. This is the one that was kind of buggy and doing weird things about the alignment stuff. Okay, so this is version 3. This is the version of the demo you saw up front. Now, this is pretty much the same as version 2, it's just been more refined a little bit. Let's run this to reacquaint ourselves. I think we've got 200 lines with 200 fragments again. The things to notice is our lines are not pulling around the edge of the space. Our glow for the header is a bit more subdued, so it's not overpowering the scene as much. And we have a gentle push in and push and pull out actually as we're doing this effect as well, which kind of adds to the illusion as well. The combination of just looping the points and the alpha addition made pretty much the effect come alive. It's not the best it could look, but you know, it works pretty well. Let's dissect it. The code is actually the same as version 2, I'm pretty sure. All I've done is I've added a secondary speed. So we're just looping from the old speed to the new speed over, it might be 5 frames or 10 frames or whatever it happens to be. And we just move to the next set of points. The initialization code's the same. I wonder what this one looks like if we take out the initialization of those points. Just out of curiosity. Let's find out together. Yeah, it's kind of nice. I kind of like that actually. We'll restore that. Something you can do for yourself. So the initialization code creates this two-dimensional buffer. Each line has a certain structure about it, where we're using these offsets here to simulate a type structure. It's not a great way of doing it, because actually when you address anything in a two-dimensional array, it has to do 2 levels of sanity checking against these fields. So they generally tend to be twice as slow. To move the lines or to update the lines, if we don't call this, we don't get anything happening at all. So for each line, we're going, hey, what's your current reset timer? We're checking the current update timer. In other words, have we reached this maximum that we're meant to have? If we have, let's reset ourselves. We'll change our speed. Do we need that? Some of that might be legacy from how it used to work. Here, this is how it used to work before. We've got this new speed equal the old speed plus a random of this change, etc. And that kind of worked okay, but it works better just to have, when our timer runs out, we compute a new vector, a new speed vector, we reset our timer, and we just swap the old new vector with the current vector. This is a change. We're going, give us how much, convert the current update time to a scalar we can use to loop between the two vectors. We update the timer after we've done that. We copy. So, I mean, even that, you don't really need to do that, do you? We're copying each of the coordinates from the line fragment, from the header to the tail. Every frame we update the very first frame, but before we do that, we copy all of the old coordinates down through its possible positions, and we add the new leading coordinate to it, if you know what I mean. What we could do is we could just have them have the available 200 points for the trail, or the tail I should call it, and we have a starting point for where the lead point actually is, and then just every frame that starting point shifts one. As it gets to the end, it wraps around to the start. That would mean you don't have to move anything for each line fragment. It's conceptually a bit more awkward, but the principle's the same. Because you wouldn't be starting from 0 to the end of the line segments. You'd be starting from the current offset within the line segments that you had last frame. As you shift forward, you're overriding the last point of the tail that's now dimmed out to black anyway. Next we do the actual moving of the lead point. Grabbing its position, we're looping, we're computing its speed in this direction. So we're going, it's a long expression, we're going, hey, give me the old vector here, here's the new vector, and just give me the scale between the points, and that will make it look like it's curving from one vector to another. We're just adding these coordinates together. Bit of crap code there. Doing a clip, making sure it's within the bounds on all three axes. So if it's within the right, left, on the x-axis, on the y-axis, the front and the back, and there's the top and the bottom, and then on the z-axis it would be the front and the back, but I've used left and right here all the way through. Build palette. This could be replaced really just with a ground strip, and then just read the pixels off the buffer. So there'd be two line fragments from white to the randomized color, and then from the randomized color to black. Here I just didn't bother, just went, I'll stuff it, and just made it do the whole, just made it from the random color all the way down to whatever the last color is going to be. In this case it's going to be black. And here it actually does, it interpolates through each one, uses dot plot and inks, and it's pretty ugly stuff in there. All right, for an overview, I think that's about where we'll have to leave it. Hope you find that useful. I hope you've picked up some new ideas. If you want to take the code and abuse the living hell out of it, be my guest. This will be posted on the forums as always. Thanks for watching, and I'll see you next time. Bye.